Okay, hello everyone. So in this video, I would like to introduce some basic x86-64 assembly programming. Um, so let's create a new file. All right. And the first thing that we want to do is always to start by typing .text. Yep. And .text basically specifies that the memory section we're working in is the text memory section, which is where the code is being stored. So we can define our string. I'm just going to name my string str, and we use .string to specify that this is a string object. And then I'm just going to type hello world. Then the next part is defining the function. So we're going to be writing the main function, and we do so by typing .global main, and in the next line main colon, and below the colon we implement the content of this function. So whenever you declare a function in x86-64 assembly, you want to use .global function name and then function name colon. So there are a few lines that every single function in assembly, in x86-64 assembly should have. First, we must push Q RBP and move Q RSP RBP. So this is to save the frame pointer. Basically, the push Q command pushes RBP onto the stack, and then move Q RSP RBP moves the content that's stored in the register RSP into the register RDP. RSP is a special register called the stack pointer. It always points at the points to the top of the stack. And then RBP is used for the base pointer. So basically, we want to store the old value of RBP onto the stack. And then after we do that, we move the value of the stack pointer into RBP. So that RBP stores the base of the base pointer. So RBP is the base pointer basically. Because when we execute a function, it's gonna have, like, there's gonna be a bottom of the stack and a top of the stack. So RBP points to the bottom of the stack, and RSP will later point to the top of the stack. All right, and then at the end of the function, for every single function, you should have leave and return. So leave is essentially just undoing the previous two commands. It's equivalent to move Q RBP RSP and pop Q RBP. So basically, we want to move the value stored in the base pointer back to RSP, the stack pointer, when we're about to leave the function. And we want to pop RBP from the stack so that we retrieve the old value. And then this old value that we retrieve will be the base pointer of the function that called main. So it would just be the parent function basically, because when we call a sequence of functions, it works as a stack. So for example, if main calls ABC and then ABC calls DEF, the function stack will look like main at the bottom, ABC on top of main, and then DEF is above ABC. And then when DEF finish executing, it gets popped out of the stack, and then we have ABC at the top of the stack. So that's why we have to save the base pointer in the beginning, and then we have to save in the beginning and retrieve the value. Okay, so these are the 4 lines that you should have in any function, and for this specific function that we're implementing, we want to print hello world. So the first thing we have to do is move the address of str. So dollar means that we're getting the address of str. We move it into a register called rdx. Now rdx is specifically a register used for passing the first argument. So this stores the first argument. And you can also use it as another general purpose register when doing calculations, but when doing function calls, the first argument has to be moved into RDI. And the next thing we do is move Q $0 into RAX. And RAX is a register that stores the return value of a function. So if we call printf, then whatever printf returns is going to be stored in RAX. So we have to initialize it to 0 before calling printf. And then we call printf by simply doing call space printf. And then this would just be equivalent to printf hello world. Okay, so this is a simple hello world program in assembly. Let's try to compile this. And I'm currently using SSH to connect to a server. We can compile this by doing gcc-static-o, and let's name our executable hello world.out, hello world.s. Okay, so now let's execute hello world.out. We see that it prints hello world. And I mentioned that leave is equivalent to these 2 commands. So let's try to replace leave with these 2 commands. Move Q RBP RSP. So this moves the value in RBP back to RSP, and pop Q RBP pops RBP from the stack, because previously we pushed it onto the stack, and now at the end of the function we want to pop the value back off the stack. So let's try to execute this. Okay, we see that it still works. All right, and then return is a command used for popping the return address and jumping to it. Okay, so basically when we finish executing a function, we need to go back to the function that called this function. And that's being done by popping the return address, which tells us where to go back to, and jumping to that address. So we see that this involves 2 steps. The first step is to pop the return address, and the second step is to jump to it. So let's comment this out. And let's say pop Q RCX. RCX is just another register, and I'm storing the return address into RCX. And then we can jump to this address. Sorry, not jump, but JMP star %RCX, which tells us to jump to the address. So if we compile this, we see this still works. Okay, so another topic that I want to cover in this video is loops. So let's say we want to print hello world like 5 times. Let's say we add %LV here, and we're going to print the index. Yeah, so basically what I want to implement here is just first we're going to initialize a variable I to 0. In this case it's going to be a long, because all the registers RBP, RSP, RBP, they're all 8 bytes long. So what I want to implement is while I is less than 5, I want to do printf hello world. Yeah, this is what I want to do. Okay, so let's use 2 Kali saved registers. So these are Kali saved registers. And what this means is that when we use a Kali save register, if we make a function call, then these values remain unchanged. The function call is not going to corrupt the values inside these registers because they are Kali saved registers. And the reason for this is because inside any function, all the Kali saved registers are being pushed onto the stack if they are being used. And then at the end, they are popped off of the stack. So that means that before, at the beginning of the function, we save the values, and at the end, we retrieve the saved values. So that's how these registers are Kali saved. So we also have to save the values inside our implementation. And if we save them by using popq, we also have to make sure that we, if we save them using pushq, then we also have to make sure that we pop them at the end in reverse order. So because we pushed R12 before pushing R13, we have to pop R13 before popping R12. This is because a stack follows last in, first out, the last in, first in property. All right, so these are Kali save registers, and to implement this, I'm going to initialize R12 to 0. All right, so this means that R12 is going to be the variable I. And for a while loop, we use a label. So I'm just going to name my label while. You can name this anything you want. And then for I less than 5, we're going to use a command called compare q. And the q in these commands, like push q, move q, compare q, the q represents that we're pushing, moving 8 bytes because all these registers are 8 bytes. Okay, so we want to execute the print statement 5 times. So let's move 5 into R13. Okay, so R13 equals the constant 5. And whenever a number is being prepended with a $, it means that just treating this as a constant. So $5, $0, they're constants. Okay, and next we're going to compare R13 with R12. So the compare q command is going to set a flag based on the value of R13 minus R12. So it's gonna evaluate R13 minus R12, and we want to stay in the while loop as long as I is less than 5. So basically this is equivalent to while R13 minus R12 is greater than 0, while 5 minus I is greater than 0, which means that we have to jump out of the while loop if R13 minus R12 is less than or equal to 0. So the LE stands for less than or equal to. And then we need to jump out of the while loop. So I'm just gonna create a new label called end while and jump here. All right. And we want to make sure that we jump back to the while label after executing the printf. And we also want to make sure that the index is being incremented. Yeah, so I would actually have an infinite loop here with what I wrote down previously. Yeah, we want to make sure that the value of I is being incremented. All right, so we can use add q $1. So we're adding 1 to R12. All right. And then we wanted to print hello world I. So that means that we need a second argument. Yeah. Okay, so RDI stores the first argument and RSI stores the second argument. All right. So now we should see hello world being printed 5 times. So let's try to compile this. All right. So we see hello world 0 all the way to hello world 4. So that's 5 times. So this program works. And I mentioned how these two registers are Callie saved registers. However, what if we don't use Callie saved registers? Like let's say we don't use Callie saved registers. So for example, let's say we use RDX and then RCX. Okay, so change all of these, RDX, RCX, RDX. Okay, so we've changed all of these. Yeah, so let's give this as a shot. Let's see if it works. Yeah, we see that it only prints hello world once. So that means that something is wrong. Okay, so let's go back to the program. So what's happening is because since RDX and RCX are not Callie saved, when we call printf, the values of RDX and RCX will get modified because printf might be using these values, using these registers, which means that the value is going to get changed. So that's not good. And we need to save the values of these two registers before calling printf. So because these are not Callie saved registers, we need to make sure to save them before calling printf. And then since we're doing pushes, we also need to do pops. So pop them in reverse order. Okay, so now we save these values. And because we're saving these values, we should be seeing the correct result. Yeah, and we see that it's working again. Okay, so I think this is already plenty of things that I covered. We start with .text, define the string, define the main function, and then always make sure to have push Q RBP, move Q RSP RBP, leave and return, and yeah. If you enjoyed this video, don't forget to like and subscribe. If you have any questions, just drop me a comment down below, and I'll see you in the next video.